A very good afternoon, morning, or evening to everyone, depending on when you might be watching this video. My name is Kenneth, and on behalf of my co-authors, I will be presenting a dataset of urban sound recordings that we curated in Singapore and have made publicly available. The dataset is called SINGA-PURA, and is a strongly labeled polyphonic dataset of urban sounds with spatial-temporal context. SINGA-PURA here stands for Singapore Polyphonic Urban Audio. And it also happens to be the Malay name for Singapore, with Malay being one of the 4 official languages of Singapore itself. With that little introduction out of the way, let me give an overview of the presentation. I will first talk about why we decided to create and publish this dataset, and compare it with existing urban sound datasets in the literature. Then, I will explain the methodology behind how we obtained the audio recordings and how we labeled them. This will be followed by a basic exploratory analysis of the SINGA-PURA dataset. Lastly, I will conclude the presentation with some remarks on the dataset and provide links for anyone interested to access and download it. Today, about 55% of the world's population lives in urban areas, and this proportion is projected by the United Nations to grow to 2/3 of the world's population by 2050. With the increased population density of urban areas, urban noise pollution is thus going to become a pressing issue for most governments and urban planners to deal with worldwide. Since noise pollution has been correlated with reduced environmental quality and increased health issues such as stress and fatigue, it is important for urban planners to monitor the levels and the types of noise present in urban acoustic environments to be able to better develop noise mitigation strategies. Collecting audio data in person is obviously time-consuming, so why not use wireless acoustic sensor networks that can record and analyze the data for us autonomously? Well, for a wireless acoustic sensor network to do so, we usually require it to detect a certain sound event of interest, or certain sound events of interest. Perhaps this could be construction noise, if we want to observe whether a construction site near a residential area is following certain noise protocols. With the rise of deep neural networks for applications related to acoustic event classification and detection, such networks generally need large amounts of labeled audio data for training. But then again, such data is generally scarce. It is possible to use synthetic data generation techniques, for instance with packages such as Scaper or Pyroom Acoustics, on a bank of pre-recorded sounds. But synthetic data runs the risk of a covariate shift that makes the results incompatible when applied to real-world contexts. Ideally, having audio recorded from real-world environments would reduce this risk, so this was our motivation to create the SINGA-PURA dataset, which we publish here as 6,547 strongly labeled and 72,406 unlabeled 10-second recordings from a wireless acoustic sensor network that we deployed in Singapore. Of course, our dataset is not the first urban sound dataset in the literature, so we compare it with 2 other publicly available urban sound datasets that are frequently used to train models for urban sound tagging. The first over here is SONYC-UST, a similar urban sound dataset with recordings from a wireless acoustic sensor network deployed in New York City. The second is Urban Sound and Urban Sound 8K, which was one of the first datasets designed specifically for urban sound tagging. Urban Sound's recordings are curated from the Free Sound database, which is a database of sounds and recordings that anyone around the world can freely upload and download under Creative Commons licenses. Hence, these recordings potentially come from anywhere in the world. The number of classes for each dataset naturally differs as well, but let me bring to attention the spatial-temporal context that is present in the SONYC-UST datasets, as well as the SINGA-PURA datasets. Spatial-temporal context basically just refers to additional metadata for each raw audio recording that contains information about the location, time, and date of recording. This context is important because there is indeed spatial-temporal dependence in real-world audio data. For instance, you are more likely to hear construction sounds near a construction site, and you are less likely to hear, for example, an engine revving in the middle of the night. This has also been found in the 2020 DCase challenge to significantly improve acoustic event classification performance, beyond only using the raw audio data. The types of labels available for the datasets also differ, as can be seen in the table in green at the bottom. Monophonic refers to the fact that there is only one sound event per recording, whereas polyphonic refers to the fact that there can be multiple, possibly overlapping sound events per recording. A weak label refers to a label that indicates only the presence of an event in a recording without any information about when it starts or when it stops. In contrast, a strong label refers to a label that indicates the start and stop time of the event as well. Clearly, strong polyphonic labels provide the maximum amount of information regarding the sound events in a recording. And that is what we have chosen for the labels in the SINGA-PURA dataset. Now, let me elaborate on our data acquisition procedure. As I mentioned previously, our recordings were obtained from a wireless acoustic sensor network that we deployed in various locations in Singapore. The network consisted of 14 units in 4 distinct neighborhoods, 2 in the east and 2 in the west of Singapore. All the units were located in public locations and were attached with either a single channel microphone, as shown in the picture on the left, or a 7-channel microphone, as shown in the picture on the right. The breakdown of microphone type and units deployed for each neighborhood is shown in the table on the left, and the labeled recordings in the SINGA-PURA dataset were all captured from the sensors over the course of 3 months, from August to October 2020. The unlabeled recordings, on the other hand, were recorded over a longer time period. With the recordings obtained from the wireless acoustic sensor network, we then had to label the raw audio with the corresponding sound event labels. A team of 5 annotated a set of 6,547 recordings that eventually formed the strongly labeled portion of the dataset, and recordings with audible sensor faults were discarded from this portion of the dataset. All the annotators listened to the recordings via the same model of headphones and at playback levels matching that of white noise at an A-weighted equivalent sound pressure level of 65 decibels. They then identified the sound events present in their assigned recordings by coarse and fine class, provided their onset and offset times, and estimated the proximity of the events from the sensor. In the case of sound events whose classes were ambiguous, all annotators listened to the recording and subsequently made a consensus decision on them. Now, what classes were of interest for the SINGA-PURA dataset then? We tried to be as comprehensive as possible with our label taxonomy and attempted to capture as many of the sound events present in the recordings as possible. At the same time, we designed the taxonomy to be compatible with the SONYC-UST dataset as well, so that users of either dataset can augment it with recordings from the other to train more generalizable models for urban sound classification or any related audio task. This resulted in the taxonomy you see in the diagram here, with 14 coarse-grained and 40 fine-grained classes. The 14th coarse-grained class at the bottom right-hand corner is labeled as Others in order to capture sound events that exist in the SINGA-PURA dataset but that do not fit well into any of the other coarse class labels. In addition, we omitted the ice cream truck class from SONYC-UST for the SINGA-PURA dataset because this sound class is not present in Singapore. We provide the raw audio recordings in FLAC format and both the spatial-temporal context and strong labels in CSV format to allow for as much universal compatibility as possible between computer systems that may be processing the dataset. With the labels and raw recordings, we can now do a preliminary analysis of the labeled data. The first question that came to our mind was, what types of events are present in the data that we collected? And these two figures here attempt to answer that question. The figure on top shows the distribution of sound events by their coarse level class. We can see that class 3, non-machinery impact, has the highest frequency of occurrence, followed by class 9, animal. The high frequency of occurrence of animal sounds in SINGA-PURA is largely due to cicadas and crickets chirping being relatively common in Singapore. The bottom figure sums the events up by their active duration instead. Notice that the distribution of duration is unbalanced, but follows an inverse power law, which is typical of that of real recordings in urban environments. In other words, there are some sounds that are heard almost always, like number 1, engine, and some sounds that are almost never heard, like class 4, power saw. We might now be interested to ask the converse question, which is how much of the data collected contains each type of event? And now, once again, these two figures attempt to answer that question. The top figure shows the distribution of the number of recordings with at least one sound event by cost level class. Since a given recording may have multiple sound events, the total number shown in all the bars exceeds the total number of strongly labeled recordings in the SINGA-PURA dataset, which is 6,547. However, the more interesting figure is on the bottom, which shows the mean sound event duration in each 10-second recording. Sound classes that are characterized by stationary or ambient sounds naturally have longer average durations when they occur. This includes class 1 engine due to the presence of traffic, and class 11 weather due to the presence of rain. On the other hand, sound classes characterized by impulsive or transient sounds naturally have shorter average durations when they occur. These include class 3 non-machinery impact, as well as class 12 break. If we look at the degree of polyphony in recordings of the SINGA-PURA dataset, we also observe that polyphony is common in the dataset, as expected from real-world acoustic environments where multiple sound sources can be present and overlapping at the same time. Lastly, we also trained a baseline acoustic event classification model with the cost labels of the SINGA-PURA datasets. The baseline model is similar to that used by the authors of the SONYC dataset and takes as input OpenL3 embeddings of the raw audio concatenated with the spatiotemporal metadata of the recording. For the SINGA-PURA dataset, we modified the output layer to output 14 values instead, corresponding to our 14 cost classes. Since the resulting model weights from the trained models, as well as their architectures are thereby different between the SINGA-PURA and SONYC-UST datasets, the results are not to be compared directly with each other, but we do note that the difference in results is also indicative of the difference in acoustic characteristics of the locations chosen for both datasets and cities. In conclusion, we introduced a non-synthetic polyphonic urban sound dataset with spatial-temporal context and strong labels, which we named SINGA-PURA. The dataset consists of recordings made by a wireless acoustic sensor network deployed across Singapore, and we designed the label taxonomy for compatibility with SONYC-UST, an existing urban sound dataset. This allows SINGA-PURA to be used in isolation as a dataset to train models for urban sound classification, as well as in conjunction with other datasets for model benchmarking as well. With that, I have come to the end of the presentation. This last slide has links and QR codes to access the SINGA-PURA dataset if you are interested. Thank you for your attention, and I look forward to any questions or comments that you may have.